Hello, I'm Gregory Massa, and today we're going to be looking at Module 9. Specifically, we're going to be covering acid-base equilibria. We are going to start off with review from the textbook and lecture content as we look at Bronsted-Lowry theory, as well as the differences between strong acids and weak acids, and strong bases and weak bases. Then, we are going to cover equilibrium constants with Ka, pKa, Kb, and pKb. After this, we're going to look at a real-life application of acid-base equilibria with vinegar and how it works when it is mixed with water to clean things. Finally, we're going to go over two practice problems. In one, we will find the pH in a solution, and in the other, we will find the pKa of a solution. According to Bronsted-Lowry theory, an acid is a proton donor, while the base is a proton acceptor, and protons are just H+ ions. In the example, we have acetic acid, which loses a proton. This makes this an acid, and the resulting species, which is acetate, a conjugate base. So there we can see the conjugate acid-base pair. Now water gains a proton. This makes this a base, and the resulting species, which is hydronium, is its conjugate acid. And we can see there that they have a conjugate acid-base pair as well. The difference between strong acids and weak acids is how they ionize in water. Strong acids are going to completely ionize in water, and this would give us a large Ka value. Whereas weak acids only partially ionize in water, so this would give us a small Ka value. Some examples of strong acids include hydrochloric acid, hydrobromic acid, hydriodic acid, perchloric acid, nitric acid, and sulfuric acid. When we refer to the differences between strong bases and weak bases, we're also looking at ionization. So strong bases completely ionize in water, and they're going to have a large Kb value, whereas weak bases are only going to partially ionize in water, and they're going to have a small Kb value. Some examples of common strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Now we are going to look at the Ka, pKa, Kb, and pKb. The Ka is the acid dissociation constant. As mentioned, strong acids have a large Ka, and weak acids have a small Ka. To calculate the Ka from the pKa, you would just take the 10 to the power of negative pKa. To calculate the pKa from the Ka, you would just take the negative log of the Ka. The Kb is quite similar to the Ka, except that the Kb is the base dissociation constant. So, as mentioned, strong bases have a large Kb, and weak bases have a small Kb. And to calculate the Kb, you would just take 10 to the power of negative pKb. To calculate the pKb from the Kb, you would just take the negative log of the Kb. Now, we're going to be looking at real-life applications of acid-base equilibria with vinegar. Vinegar is also known as acetic acid, and acetic acid has a chemical formula of CH3COOH. There are many different ways you can use vinegar, as you can see to the ad on my right displaying that there are over 70 plus wonderful vinegar uses and benefits. It is used in the preparation of many foods, including salads. It is also used in the preparations of sauces, including hot sauce, mustard, ketchup, and many other of your favorite sauces. Finally, it is also used in cleaning. It can be mixed with water to remove stains, and it can also be used to remove rust. So how does acetic acid work? Well, we're going to be focusing on when acetic acid is mixed with water. So when mixed with water, this will produce hydronium and acetate. The hydronium bonds to molecules that it encounters, which weakens the molecule structure. This is great for cleaning stains from alkali substances such as soap and urine. Acetate has an extra electron, as we know from its negative charge, and this is going to bond with other atoms, especially metals. This is great for cleaning rust and grime. When mixed with water, acetic acid is also good for killing odors caused by bacteria and fungi due to its acidic nature. Now, let's look at the chemical reaction. As mentioned, acetic acid is going to react with water to produce a hydronium ion and acetate. The Ka value for this reaction is 1.76 times 10 to the power of negative 5, and that's at 25 degrees Celsius. The pKa is 4.75. From these values, we know that this is a weak acid, so little dissociates. However, enough of it is still able to dissociate to where it is able to get the job done for cleaning stains, dirt, rust, and grime. Now, we're going to be looking at a practice problem that pertains to acetic acid mixing with water. The question is, what is the pH of a solution containing water and 1.25 moles per liter of acetic acid? The first step when doing any of these types of equations is to write out the equation. We did this on the last slide, so I won't go over this. The next step is to set up an ice table. We are given the initial concentration of acetic acid, which is 1.25. We don't need to worry about water because it is in a liquid form. And in initial conditions, hydronium and acetate will have concentrations of 0 moles per liter. Now the change for acetic acid is going to be minus X, and the change for hydronium and acetate are going to be plus X. This will leave us with final equilibrium concentrations of 1.25 minus X moles per liter for the acetic acid. We don't need to worry about the water again. And the hydronium and acetate will each have X moles per liter for their concentration at the equilibrium. Our next step is to set up an equilibrium constant expression and solve for X. We know that our equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. So we have the concentration of acetate multiplied by the concentration of hydronium, all divided by the concentration of acetic acid. And we ignore water because it is in its liquid form. Now we know from one of the previous slides that the Ka is 1.76 times 10 to the power of negative 5. We know that the concentrations of both acetate and hydronium are X, and that the concentration of acetic acid is 1.25 minus X. However, because our Ka value is very small, we can assume that X is also going to be very small, and therefore we can not include it. So we just have X squared over 1.25. After some solving, we get that X is equal to 4.69 times 10 to the power of negative 3. Our fourth and final step is to find the pH. We know that X is equal to 4.69 times 10 to the power of negative 3, and that the concentration of hydronium is equal to X. Using this, we can find the pH by taking the negative log of the hydronium concentration, and this will give us a value of 2.34. Therefore, our pH of this solution is 2.34. We're going to do one other practice problem. This time we're looking for the pKa of a 0.0145 moles per liter solution of HNO2 that has a pH of 2.34. I won't go over these first two steps in as much detail since we already did them in the last problem. So our first step is to write out the equation, and our second step is to set up the ice table, showing the initial concentrations, the change, and the equilibrium, and leaving out water since it's in its liquid form. For our third step, we're going to solve for X using the pH, which is 2.34, and then we're going to solve for the concentrations of the reactants in the products. We know that X is equal to the concentration of hydronium, and the concentration of hydronium is equal to 10 to the power of negative pH, which in this case is 2.34. When we put that into the calculator, we get 0.0046 moles per liter. We also know that the concentration of NO2 minus is equal to the concentration of hydronium. So we're also going to get a value of 0.0046 moles per liter for that concentration. From the ice chart, we know that the concentration of HNO2 is equal to 0.0145 subtract X. In this case, X is 0.0046. So when we put that into our calculator, we're going to get a value of 0.0099 moles per liter. Our fourth and final step is to set up the equilibrium constant expression and solve for Ka, and then finally we're going to find the pKa. So when we put in those values into the equilibrium constant expression, we're going to get 0.0021 for our Ka, and since pKa is equal to the negative log of the Ka, when we put that into a calculator, we're going to get a value of 2.68 for the pKa. To summarize what we have gone over today, we started off by looking at Bronsted-Lowry theory and how acids are proton donors and bases are proton acceptors under this theory. We also looked at strong acids and bases versus weak acids and bases, and how strong acids and bases have a large K value, while weak acids and bases have a small K value. We then went over the Ka, pKa, Kb, and pKb, and how to calculate those values, before going over the chemical properties of vinegar, as well as how it works and other applications of it. And finally, we went over practice problems for solving for the pH and the pKa. Thank you for listening.